the last thing that we did was show that every infinite subset of a countable set is itself countable. Right? Every infinite subset of a countable set is countable. Right? And it has to be infinite because you don't want to have some finite subset. Right? You don't want your set to be finite. Okay. That's where we stopped. That's where we stopped. And so there are a couple more things that we want to say. First is that if you have a countable set and you let B be some finite product, some finite Cartesian product of the A's. Okay. In other words, it will be vectors, right? Vectors where each component is an A. Okay. Then let's call this thing B sub n. Then B sub n is countable. Okay. Then this Cartesian in brief, a Cartesian product of countable sets is countable. So you've got a bunch of you have a Cartesian set. I'm sorry, you have a countable set. You take a Cartesian product of these guys. You make vectors out of them, and then that set of vectors is going to be countable. Okay, Mia, you're smiling. Yes.
Not a real question. Just
yes.
It feels like we're none of this countability is like what we would normally mean when we say countable. So what are we trying to get at when we say it? Like I understand the definition of countable.
Yes, but what do you mean it's not? You mean it's not? What do you mean in English when you say countable?
Finite.
Finite. Oh, okay.
Right.
Yeah, no, that's not what we mean.
Yeah.
No, we mean either finite or has a one-to-one correspondence with the natural numbers.
Yeah. No, that's why I was smiling. Sorry.
Okay. Very good. Okay. Okay. Can anybody? What's the proof of this? So you all should have. You all have read it. It's not. What's the idea of the proof? Right. Let's just do one case, for example. Let's do the case n equals 2. Okay. Okay. So in other words, we're looking at things that look like A1, A2, where the AI are an A. Right. Why is that a countable? Why is that countable? Okay. You know that the set A is countable. Okay. You know that the set A is countable. Okay. Anyone remember the proof of this, or can I just imagine the proof of this? Bruin.
Is this the rectangle?
Is this the rectangle? No, this is not. Are you thinking of the Cantor's diagonal process?
Yes.
No, this is not it. No. But the idea is simple. You just say, well, look, if you look at the set AI cross A, okay, so the set AI cross A, you fix one of the numbers, fix one of the elements, cross it, right? In other words, we're looking at everything that looks like, so let's look at, say, A1 cross A. So A1, comma, you just fix some element, okay? A where A ranges over A, then this is a countable set, right? Because the first element is fixed, and the number of elements is the same as the number of elements is the same. The cardinality of this is the same thing as A, right? And A was countable, right? Okay, so you know that this is a countable set, right? Is everyone okay with that? This is a countable set because this thing for any A1 in A, this thing has a one-to-one correspondence with A, right? Just use the second element. Right? as the amount. Okay. And then B2, well, B2 is just the union of all a union of all these guys, right? So B2 is just the union over all elements of A of little a cross A. Right? So it's a countable union. It's a countable union of countable sets. The end. Okay. So simple, right? Some of you are looking kind of dull. Is it because you're not anybody not understanding? Anybody confused? Anybody willing to say that they're confused? Okay. Okay. So okay. So and then if you want to do for higher guys, then you can basically do it by induction, right? So for the nth guy, you'd say, well, you've proven it for the first, you would assume that Bn minus 1 is countable, and then just use the same argument to bootstrap your way up to Bn. Okay, so just by induction. So general case of Bn can be done by induction. Right? You would just, know it's true for B1, and then assume Bn minus 1 is countable, and then use exactly the same argument to show that then Bn is also, right? And then those two things together would give you the inductive proof. So then, okay. So that's how you do that. Okay. So there was one of the questions in your that people sent in the other day was, is Q countable? Is Q countable, right? And the answer is, yes it is, right? And one way you can see it is by using this, as they note in the book, right? One way you can see it is by using this, this theorem, right? So you say, well, look, consider Q cross Q. Consider Q cross Q. I'm sorry, not Q cross Q. Consider Z cross Z. Right? That's countable. Right? So everything that looks of the form PQ, where P and Q are integers. Okay. Then we can identify Q with a subset of Z cross Z. Right? Because every element of Q is of the form P over Q, where P and Q are integers. Right? So just use, for every element of Q, just map that, make a map from that to P comma Q. Right? So you're going to get a subset. You get a subset of Z cross Z. Right? Yeah, please don't use your phones during class. Yeah. Okay. Yeah. Please unplug yourselves. Pay attention. Okay. Yeah. So what do I say at this point? You've got this thing. Q is identified with a subset of Z cross Z, and then Mia.
Oh, I would just
Exactly.
point to the theorem.
Yes, just point to the theorem, and that's the end, right? So Q is a subset is an infinite subset. It's infinite. It's Q. Q is an infinite subset of a countable set, and so it is itself countable. Right? Yes, Fernando.
So when we're trying to prove a set to be countable,
Mhm.
and we do find another set that the set that we're interested in is a subset of the other set, which way should the mapping be?
You want this to
Yeah,
be
so for this case, we want
Yeah.
to prove Q
is a subset of a
is a
countable
countable
set.
of Z cross Z.
Yes, that's right.
But which way of the mapping should it be? Should it be have function from Q that maps to Z cross Z, or the other way around? Or either one would be fine.
Well, you're identifying Q with a subset of Z cross Z, right? So this Q is, you're going to think of Q as, you're going to have a map. I mean, you have a map taking, you have a one-to-one, you have a map taking Q. You have you have a one-to-one map taking Q into Z cross Z, right?
And
rather
it
than
doesn't
the opposite.
It doesn't have to be onto, right?
No, you
Okay.
don't need it to be, right? Because all you need is to have Q as a subset of Z cross Z,
I see.
not as all of Z cross Z. In fact, it won't be all of Z cross Z because you're not going to hit
Q
the guys
equals
with
zero.
0 in the second entry. Yeah, Jonah.
You say exactly what you mean when you say Z cross Z. It's just the fact that you're dividing a Z by a Z number by a Z.
When I say Z cross Z, all I mean is just like when we talk about R2, being R cross R, it's just pairs of elements. Yeah, just pairs of elements. That's all we mean when we say this cross. Yes.
So are we assuming that the set of integers are countable?
Yes. Yes, because can you make a map from the integers to the natural numbers? I mean, can you make a one-to-one map going from here to here? Or in other words, can you put the integers into a unique list? And that's clearly true, right? I just say 0, 1, -1, 2, -2, 3, -3, and so on and so forth, right? And so if you can put them into a list where there's no repetition, right? Then you've got your map. So yeah, it's very clearly countable. Okay. Any other questions? Any other questions? Okay. So so what we see is that if we take these Cartesian products, then a Cartesian product of countable sets is still going to be countable. But then you could ask, what happens if you take an infinite Cartesian product, right? So we've been doing it for a finite. We said, for a finite Cartesian product, that's fine. Right? But what about an infinite Cartesian product? In other words, what if you take, basically just sequences of elements in a countable set, right? And the simplest one, for the simplest one, so what we'll do is we'll say, well, let A be the set 0, 1. Okay, so you have only two choices, 0 or 1, right? And then, I'm sorry, let me not call it A. Consider the set 0, 1, and let A be just all sequences, a set of sequences whose elements are either 0 or 1. Either 0 or 1. Okay. Okay. So this is the same thing as thinking of this set cross itself infinitely many times. Okay. Now you've got like infinitely long vectors where the entries are all 0 or 1, and the claim is that this is uncountable. Okay, and this is sort of a famous argument. It's not really useful anywhere else, but this is a famous argument, so you might as well know it. Cantor's diagonal process. So what's the idea? Can somebody tell me Cantor's diagonal process? Varun, you seem like you know it.
it's you can like lay out the elements in like a vertical and horizontal direction, and then the I don't know how to explain it properly, but then like
That's okay.
the diagonal is like how you count them or something. I don't know what I'm saying.
Somebody help Arun. Somebody throw him a line. What's your name, please? What's your name?
JP?
JB. What's the Cantor's diagonal process? Right. So the proof is, suppose it is countable. Suppose A is countable. Right. So you got it. Right. Suppose A is countable. So you've got a list of sequences. You can make a list of sequences, right? You can make a list that is going to hit everybody. Mia, do you want to say it?
Oh,
Would you like to
I only remember the beginning of the proof, but sure.
Suppose A is countable. No.
Yeah, right. So right after,
Okay,
then
yes.
you go through.
Yes, exactly.
You go through each element, which is each a sequence, right?
Yes. So A1 is some sequence. Say it's suppose its entries are A11, A12, A13, A14, blah blah blah.
And then
Right.
If-
A2 is A21, A22, A23, A24, blah blah blah, and so on and so forth.
so then you go if A11 is equal to 0, then you set A1 equal to 0 or something, and then if A22 equals to 0, you set that equal to 0 or something like that.
Yes.
Yes.
So so if A is countable, the point is this, right? If A is countable, then there exists a list of all, a list, this thing here, of all such sequences. Right? Then we have there's a complete list, and it can be, it can be written down, the first element, the second element, third, fourth, fifth, etc. Right? Okay. But in that case, lay them all out like this. Lay them all out like this, and construct a new sequence. Construct a sequence BI where Bij is not equal to AJJ. Okay, I'm sorry, let me just call it B. Construct a sequence B, B being B1, B2, etc., where the jth term is different from the diagonal jth term. Okay, so if this guy is 0, then we're going to choose B1 to be 1. Right? If this guy is 1, we choose B2 to be 0, and so on and so forth. Right? Then the sequence B is not equal to any AI, right? Because it differs from each of those other sequences at the ith term, right? It differs from the first guy at the first term. It differs from the second sequence at the second term. Difference from the third sequence at the third term, and so on and so forth, right? So that means that B is not on the list, right? But we said that we have a complete list of all sequences, and we've just created somebody who's not on the list, so that's a contradiction. I don't know.
So what if AJJ doesn't exist? Like if you have a sequence of zeros and ones that is 0, 1, 1, and it's the fifth element, it's the fifth sequence that you're dealing with, and it doesn't have a fifth
These are
element.
infinite sequences, so
Okay.
it's like, these are all infinite sequences.
Okay.
Yeah. Right, because we're not, when you consider this this Cartesian product, you're not allowed to say, I have a vector, but some of the vectors are short.
Okay.
Okay, they're all the same length. There's another question. Read.
Yeah, answer.
Okay, good. Okay. Okay, so that is the proof that that this is an uncountable set. And it's also a proof if you think about the binary representation of numbers. So if you, instead of using decimals, you represented numbers using, using binary, it shows you that the numbers between the numbers between 0 and 1 are uncountable also. Okay. So like if you look at the real numbers between 0 and 1, they correspond to some subset of this, and this thing is uncountable. So actually, they themselves will be uncountable. Okay, so that's enough about countable and uncountable. Question? No? Okay. Okay, so actually let me erase the whole board. We're entering a new section. Okay, so the next topic is this thing called metric spaces. Are you okay, Joanna?
Yeah.
Yes, okay. Okay, so metric spaces, and the point of this this idea is that a lot of the concepts that we're going to deal with and a lot of the results that we're going to get in the near future don't really depend on the fact that we're working with the real numbers. They don't really depend on the fact that we're working with the complex numbers. They would hold in a more generalized setting, one called metric spaces. Okay, so we'll have a space, and then we'll have a notion of distance. Okay, and that's all we need. But we do need to say what we mean by distance, right? So what exactly counts as a distance? For us, in R, our standard distance, the distance between 2 points, we usually take as this, right? The absolute value of the difference, right? In Rn, right? The difference between the two vectors is the norm of the difference of the vectors, right? So the distance, right? The length of the vector, the length of the vector that goes from one endpoint to the other, right? So that's these are standard distances, but a lot of, like I just said, a lot of what we're about to do doesn't depend on these specific notions of distance, but just on certain properties of distance. Okay, so we generalize the notion of distance to something called a metric. Okay, I have tried to change the name of this course from Principles of Real Analysis to Principles of just Analysis, but never been able to pull it off. I protest the name of this course. It's incorrect, right? Because we don't care about the real numbers, right? We don't care about we don't care about the real numbers. We're in metric spaces. Okay. I always get objections. Oh, why should you change the name? We should change the name. The name of this course is Principles of Mathematical Analysis. Okay, so metric spaces. You start off with a set, X a set, and then you have this function d from x cross x into R, some function. If for all points, pairs of points in X, right? All pairs of points in X, the dpq is bigger than 0 whenever p is not equal to q. pp is 0. 2, the dpq is the same as dqp. And 3, dpq is always less than or equal to dpr plus drp for some drq, drq for some third point r. if all these things happen, then we call D a metric. Right? We call this function a metric. Okay, so metric is just a distance. Okay, and we call and the pair x comma d a metric space. Okay. Okay, so like I just said, so the standard examples of the metric space are Euclidean space with dpq defined as the the magnitude, right? Your standard magnitude, right? And you see that the magnitude satisfies this, right? The length, right? The distance between any two points is bigger than 0. It's going to be 0 if those 2 points are the same, if and only if those 2 points are the same. The distance 2 points, it doesn't matter what order you take them. And then the distance from one point to another is smaller than the distance from that point to some intermediary point plus the distance from that intermediate point to the last guy. The triangle inequality, right? Which we saw held earlier for absolute value. Okay. For the absolute. Okay, so that's one example of a metric. Another sort of cute example is the taxicab metric in let's say R2. Can you do an Rn? So that is where the distance between 2 points is the length, not the length of the diagonal, but the length of the sums of these sides here. Okay, so you're in a taxi cab, and the taxi cab cannot go diagonally, right? It can only go horizontally and vertically. Okay, so how far is this building from that building? Well, you have to go this way and then that way. So this is the distance. This is the taxi cab metric. Okay, and you see, it's easy to see that that it's an easy exercise to see that notion of distance. Right, so this would be the distance between x and y is x1 minus x2 plus y1 minus y2. Right, if this point is x1, y1, and then this point, sorry, this point is x1. Sorry, let me write it. x1 minus y1, x2 minus y2. If this point was x1, x2, and this point was y1, y2.
Why did you choose that notation?
Why did I choose that notation? Because I called this guy x and I called this guy y.
Oh, okay. Okay.
Sorry.
I was thinking Cartesian.
Yeah. That's the trouble. Because I called this guy y, I basically I screwed myself over at that point. Okay. Okay. Okay, so metric, right? Space, metric space. Okay. Some basic definitions from for Euclidean space. You know what these guys are, right? Open interval, right? Half open interval, closed interval, right? So that you know, right? In R1, right? In Rn, you have a generalization of that. So say you have a bunch of numbers, ai less than bi, where I goes from 1 to k, right? So you've got a bunch of, basically what we're setting ourselves up for is a bunch of intervals. Okay, so you've got a bunch of intervals, and then you take the Cartesian product of those guys, right? This thing's set of x in Rk, where xi is less than ai, and I'm sorry, it's bigger than ai and less than bi. This thing is called a K-cell. It's just like a, it's just a box, right? It's just a parallelepiped, right? You've taken A1, B1 cross A2, B2 cross A, K, B, K. You've taken you've taken the product of all these open intervals.
In RK, how does greater than or less than, how do you determine that?
These guys are all numbers,
Yeah.
right? X is in RK. It's the guy whose components, whose entries are x1 through xk, right? So all we're saying here is, like, if I say 1, comma 2 cross 1, comma 3, right? Then all that means is that I'm taking this interval and you're crossing it against this interval, right? And you get this open box. You get this box. Okay, right? The first entry has to be in the first interval. The second entry has to be in the second interval. Okay. So yeah, don't get confused. These guys, the xi are not in RK. X is in RK. Okay. Okay. Third notion. You have some x in Rk, and you have some real number r. Okay. So if I ever say something like this, r is greater than 0, then I'm talking about a real number. So some real number r. We define, so let B r x denote all points in Rk such that x minus p in absolute value is less than r. And this is the open ball, centered at x with radius r. So this is just the notation. Right? It's all points whose distance from x is less than r. Right? So it doesn't include the surface. It does not include the surface of the ball. Right? You have this point x, you have radius r, right? You don't include the boundary of it. Okay. If we want to include the boundary, then we usually notate it with a bar over it. So this would be the guys whose distance is less than or equal to r. It's called the closed ball. These are basically just examples of what's going to follow. So basic topological notions. So now we're going to give a bunch of definitions that are sort of the basic vocabulary of topology. They will seem a little bit strange, but you'll get more and more comfortable with them in time. But at the beginning, they're always a little bit confusing. You may have noticed in my reply to the questions of day 4, I made a reference to Hitler learns topology. Did anyone look at Hitler learns topology? No? Okay, some of you did. Okay, good. So it's a parody from some German movie. In the German movie, I think things are going badly for Hitler, and he calls all these people in and like gives them this lecture where I don't know the story, but he's clearly upset. But clever people have taken this movie and dubbed it over as Hitler lecturing a bunch of topologists, and he's been spending his time trying to learn points in topology that you're about to get, and he's upset with how the topologists have done it. At one point, he says it's not even clear to me that there could be, you could even have a set that's open and closed. And then one of the people says, mein Führer, there is such a set. It's called Kloppen. And he's just he blows out and he starts swearing at Okay. So welcome to that world. Here we go. Okay. So you have X a metric space. Okay. So leaving Euclidean space behind, you just have a metric space. You have a notion of distance. Okay. So the analog of this ball is going to be what's called a neighborhood. So you have some point in the space, and again you have some positive real number. Let n sub rp be all the points in the space whose distance from p is less than r. Right? Whose distance from p is less than r. Right? And it's the same thing as a ball. Right? This is called a neighborhood p with radius r. Neighborhood of p with radius r. Okay, so for example, if you are here in R2, you're here in R2, and I say, what's the neighborhood of radius 1 with respect to the taxicab metric? Right? What's the neighborhood of radius 1 with respect to the taxicab metric? So certainly I can go this far, and I can go this far. I can go this far, and I can go this far, right? But I can also go like half here, like half distance this way and half up, right? I can go, 3/4 this way, right? So what is it? It's going to be this set here, right? This would be the neighborhood of that point with respect to that metric. Right. Okay, so just get used to the idea that your metric is not Euclidean metric. Okay. Definition number 2. You have some subset E, a subset of X, and P an element of X. If every neighborhood of P contains a point Q not equal to P, such that Q is in E, then we say P is a limit point of E. Okay? A limit point of E. So you have a set. Okay, let me introduce some convenient notation. If I put a star on the neighborhood, then what I mean by that is the neighborhood, but excluding the center. Okay, what I'm going to call that the punctured neighborhood. Punctured neighborhood. Okay, so it's the ball, but the center is removed.
That's the star.
Yeah, so that if I put a star on it, then I mean the punctured neighborhood. It's a neighborhood, but with a hole in the middle. Okay. So if I want to write, I can write this more cleanly. I hope that for every r bigger than 0, every punctured neighborhood of P intersect E is non-empty. Right? For every radius, every punctured neighborhood of P intersect E is non-empty. In that case, P is a limit point. Okay, right? Because it's the same thing, right? Every neighborhood of P contains some point not at the center, right? Contains some point not at the center that is in E, right? In other words, every punctured neighborhood, right, is going to intersect E somewhere. So it's the same. Okay. So for example, right, if we are so just as a simple example, suppose I look at the open ball in R2, Euclidean space, the standard metric, right? And I take a point inside the ball. Well, that would be a limit point, right? Because every neighborhood of that point, contains some element of E that's not the center. Okay, so those are sort of obvious limit points, right? One less obvious would be anything on the boundary, right? Because then you say, well, look, any neighborhood contains a point not the center that is in E. Okay, so this guy on the boundary, although he's not part of the set itself, is one of the limit points, right? It's not part of the set, right? Because the set doesn't contain its boundary, right? But every neighborhood of it intersects the set in a point not the center. Mia.
So the only time that something wouldn't be a limit point is if it was defined in such a way that it was like super isolated from everything else.
That's right. So what would it mean to not be a limit point? That would mean that there is some neighborhood whose puncture does not intersect E. Okay, there's some neighborhood whose puncture does not intersect E. So for example, let's go on to like a one-dimensional example. Suppose I look at the set 1 over n, where n is like this. Okay, so here is 1, here is 0. Right, so I've got 1, I've got a half, I've got a third, a fourth, and so on and so forth. Right? Is this a limit point? Is 1 a limit point of this set?
No, because it's in the set.
You can be in the set and still be a limit point. Doesn't matter.
Nope.
No, because if you choose a radius like smaller than half, then it will not.
That's right. So just say, well, look, I can find a neighborhood, and the punctured version of this doesn't intersect the set. Right? So in fact, none of these points are limit points. Right? None of these guys that I drew up here, none of the elements of the set are actually limit points. So none of the 1 over n's is a limit point. Okay. But this set has a limit point. What limit point is it? Where is the limit point for this set? 0, right? 0 is a limit point. It's not a member of the set, but you see that no matter what neighborhood you take, if you puncture it, of course it doesn't matter. It'll intersect. It always intersects the set. Right? And notation we let E prime is defined to be the limit points set of limit points. Limit points of E. Any questions? Okay. Any questions? Okay. Okay. Definition number 3. There are 10 of them. People need to take breaks from this. Yeah, if P is in E, but P is not a limit point, is not a limit point of E, then we say P is an isolated point, of E. Right? Which makes sense, because it means that there's some neighborhood where the punctured neighborhood doesn't intersect the set. Right? In other words, you in the middle are the only element of the set, of your set, in that neighborhood. Okay. Right? Right? So this term isolated makes sense. It means that being isolated, not being a limit point, but being part of the set, means that if you shrink down your neighborhoods, at some point you're going to be only one from your set in that neighborhood. Okay.
Is that true of every set?
That there's always isolated points? No.
Yeah.
No. It's just we're just saying these sorts of points are called isolated points.
Okay.
They may or may not exist.
So like in the set you drew to the left, there's no.
Yeah, here there's no isolated points. Right.
But-
Here everybody's an isolated point. Right. Okay. Number 4. If every limit point of E is in E, we say E is closed. If every limit point of E is in E, then we say E is closed. So this, for example, is not an example of a closed set, right? Because it doesn't contain its boundary, and the guys on its boundary are limit points. Okay. So this thing, which of course is called the open ball, is not closed. Okay. So those are probably the ones that are more tricky. The definition of getting up to the notion of a closed set. Then there's a bunch of definitions that get us to the notion of open. Okay. These I think are sort of easier to intuitively easier. So again, you have this. So if there exists a neighborhood, if there exists some radius such that nRP is contained in E, then we say, then we call P an interior point of E. Okay. An interior point of E. So what this is saying is that you have some set, and you have some point, and there is some neighborhood that is centered at the point, and it's contained entirely in the set. Right? There's some neighborhood that is in the set and is centered at your point. Then we call this guy an interior point. Okay, so P is called an interior point. Okay, again, this would not be an interior point. This would not be an interior point, right? Not interior because I can't find any neighborhood. I can't find any neighborhood that's contained entirely inside the set. Right? No matter what I do, I can't find a neighborhood that's contained entirely inside the set. Okay. So these guys are not interior. Not interior. This guy is interior. Okay, number 6. If every point of E is interior, we say E is open. E is open. So for example, the open ball is an open set. Because every point in it, whatever point I have inside there, well, I can find a neighborhood that's contained entirely inside the set. Okay. Number 7. This is sort of a standard definition. When we say E super C, what we mean is the complement of the set. So it's all the points in the space where X is not in E. It is called the complement. Of E. Okay. There's a definition of something called a perfect set. I'm just going to skip that. That's not too important. So the perfect sets. I don't think we're going to need it. Number 9. If there exists a point and some positive number such that the distance from any point in the set is less than m from Q, so for all P in E, then we say E is bounded. Bounded, right? So all this is saying, pictorially, all this is saying is that there's some point Q and there's some radius m, right? There's some radius m, and your set lives inside of that ball. That's all it's saying, right? Your set lives inside of some ball, some finite ball, right? Every point P in the set is distance. The distance from those points from Q, of those points from Q, is less than m. Okay, so then we call it a bounded set. Yep, read.
Can you have a set that's bounded and open? Can you have a set that's open
Sure.
and bounded?
Sure. Sure. Like, I mean, this open ball is bounded, right? Because, I mean, it lives inside some other larger ball, and it's open. Right? It's an open set, and bounded basically means not heading off towards infinity.
Yeah.
Okay, right, with respect to the metric. So here in the standard Euclidean metric, this guy is open and he's also bounded. Nothing, those notions aren't contradictory. And then the last notion, if every, so you have some set E that lives inside, the metric space X. If every point of X is either in E or a limit point of E, then we say E is dense in X. E is dense in X. So you remember earlier we talked about this result that Q was dense in R, right? And it's in this sense what we showed earlier gives this result, right? Either every point in R is either rational or it's a limit point of the rationals, right? Because if you're an irrational number, you can take an interval around you, and then by the density theorem that we proved before, you know that there's some rational number in that interval. Remember, like the previous thing said that you take some arbitrary number, and then you take something a little bit bigger than it. Then you're guaranteed a rational number. You're guaranteed a rational number between those two guys, right? What's this saying? This is saying that in every neighborhood of every real number, there are rational points, right? So what it says is that every real number is a limit point of the set of rational numbers, right? So the rationals are dense. Okay, so that's why we call that thing dense. Okay, so these are the basic definitions. Anybody have questions? Let's go on. Okay. So I'm going to leave as an exercise the result that every neighborhood is an open set, is open. In a metric space, every neighborhood is open. It's an exercise. It's short, it's simple. Instead, let's go on to something more interesting. If P is a limit point of E, then every neighborhood of P contains infinitely many points of E. Okay. Every neighborhood is going to contain infinitely many points of E. Okay. So remember what a limit point is, right? Limit point, you have this point. Every punctured neighborhood intersects the set. Every punctured neighborhood intersects the set, right? So, right, P being a limit point means that every given any R, n punctured around P intersects the set E, right? So if I take a radius of 1 to start off with, say, I know that there's somebody in here, not at the center, who's an element of E. Okay. Why do I know that there are infinitely many guys from E in there? Right? I know that there's this one guy here. You could do this sort of constructively by induction. You could say, well, should I let you think about it? No, maybe not. You could say, well, so I'm going to take a second neighborhood, right? I'm going to take a second neighborhood whose radius is smaller than the distance from P to E1. Okay, so E1's not in there. E1's not in there, right? P being a limit point means that there must be somebody in there who's from E, right? So call that guy E2, right? And so on and so forth. Right? You could do this by induction. Right? So you can construct it. Right? So let R be 1, then there exists some E1 that lies in NR1 punctured P intersect E. Then let R2 be the distance from P to E1. Then there exists an E2 not equal to E1 in an R2 punctured P intersect E, and so on and so forth. Properly, you should do this by induction. Use induction. Okay. Or, if you wanted to do it by contradiction, suppose some neighborhood contains only finitely members, only finitely many of the elements of E, right? Say E1 through En, right? So there would be this point P, and there's some neighborhood, and there's only finitely many elements of E in there. Then you get a contradiction, right? Because you just say let R be the minimum of the distances from P to e to the EI. Right? Take the smallest distance and take that as the radius of a new neighborhood. But then there would be nobody from E in there. And that's a contradiction because this P was supposed to be a limit point. Right? Being a limit point means that every punctured neighborhood intersects E. But we've just created a neighborhood that doesn't intersect E. So contradiction. Right? Then N R P intersect E is empty. Contradiction. Okay, let's try to squeeze in one more result, which is kind of nice. A set E is open if and only if E complement is closed. Let's go forwards. Let's suppose E is open. Right? In other words, it consists only of interior points. Right? And we want to show that E complement is closed. So we want to show the complement is closed. In other words, that it contains all its limit points. All its limit points. Okay. So let X be a limit point of E complement. Well, if you're a limit point of E complement, then every punctured neighborhood is going to intersect E complement, right? Then, for all radii, the punctured neighborhood around X intersects E complement. Right? Every punctured neighborhood is going to intersect E complement. Right? So it intersects the complement. But that means that the neighborhood is not contained in E. Right? That neighborhood, those neighborhoods, all of those neighborhoods are not contained in E, right? Because they intersect the complement. Right? They intersect the complement, so they're not contained in E. Right? But that means that X is not interior to E. Right? But E was open, so every point of E has to be interior. Right? E was open, so X cannot be in. Right? E being open has only interior points. Okay, everybody all right? Even if you're not all right, I'm going to go on. There's only one more minute left. Sorry. Okay. So going backwards, let's say that the complement is closed. Okay. And we want to show every point of E is interior. Okay. So say X is in E. Let's choose a point in E. We know that X cannot be a limit point of E complement. Right? E complement is closed, so it contains all its limit points. Right? E complement closed, so X can't be a limit point. Right? Okay. If it's not a limit point, that means, if not being a limit point, means that there's some neighborhood of it, right? There exists some neighborhood of it where the puncture of that neighborhood intersect the complement is empty. Right? Right, that's empty. So that means that this thing, i.e., this neighborhood, is contained entirely inside of E. Right? Because that thing, it doesn't intersect E complement, so it must be inside of E. Right? Well, that, right, X was in E, and the punctured neighborhood around X is in E. So that tells you that the whole neighborhood, MRX, is inside of E. In other words, X is interior to E. X is an interior point of E. Okay. Okay, so this gives us another way of thinking about what it means to be open or closed, right? Closed, if you don't like the limit point definition, you can just think, well, what closed means is that my complement is an open set. In other words, the complement, all the points in the complement are interior to that complement. Okay. Okay. But you will need to know, you're going to need this limit point idea often. So don't think you can get away from it. Okay, that's it for today.